All right, welcome back to another episode of the National Weather Service Columbia podcast. I'm your co-host, Matt Gropp.
And I'm your co-host, Pierce Larkin, and we are here gathered at the National Weather Service in Columbia office to bring you another fire episode
Of the podcast, yeah.
of the podcast.
Yeah.
Not a forecast discussion this time.
No.
If you watched our, you have to watch this on our YouTube page, I guess. But, if you caught our last episode, it was a great forecast discussion. Hopefully you learned a thing or two.
Yeah, we're going to plan to do some more of those in the future.
Yep.
Anytime there's a weather event on the horizon, just talk about the forecast process.
Yep.
And we'll probably do some that range in depth from more of a basic level to a more advanced level.
Yep.
Kind of just go as we see for the event. So today we're going to do our usual segments here with our word of the day. Go into an interview with the warning coordination meteorologist John Q here
The man, the myth, the legend.
Yeah, and then go into an overview of severe weather in general.
Yep.
It's kind of a prelude to our next episode where we're going to talk about the April 27th, 2011 super outbreak, which was kind of a watershed moment in really meteorological history, where we kind of had a whole paradigm shift from thinking about tornadoes as primarily in the plains to becoming more of a southeast thing.
Yeah, it was an awakening, if you will.
It was. It really changed how everything about meteorology over the last 10 years, where funding is gone, where we've been studying more and more.
Where the Weather Service has gone into more decision support and communication with the public. So
it's kind of the part, 0.5 of that episode. We're going to get more into it next week. We're going to do an interview with the meteorologist in charge here at Columbia, Rich, who is going to talk about surveying one of the EF5 tornadoes.
Yep.
That'll be a cool one. He's one of the few people in the Weather Service still that's actually had the unfortunate to be able to survey one of those events. But they haven't been one since 2013, so it's pretty rare to be able to interview someone who was able to survey that. But then back to today, we got really sidetracked there. We'll finish up with our hot weather take, and we're going to talk about different types of storm morphologies. Pulse severe versus supercells, and we'll talk more about that throughout the episode.
Which one's the best and which one's the worst?
Yeah, from a
interest perspective.
Yeah, from an interest and a forecast perspective.
Yeah, definitely.
Okay, so give us the word of the day, Pierce.
The word of the day today is really right in line with our theme of this episode. Supercells. That's right, supercells.
Yep, supercells. So we're talking cells here like convective cells, and this is a super one.
Yeah, it is a supercell. Sometimes you go to a superstore and it's just a bigger version of the store. Well, guess what? A supercell is not necessarily a bigger version, but it is a more intense version of a regular cell.
So it's not like a supermarket at all.
No. Yeah. I mean, you're not going to go get groceries at a supercell. Don't worry.
No.
But
anyway,
what you are going to do...
Get back on target.
I am.
Ready?
I'm on target. Let's go. What you are going to do at a supercell is you're going to witness a rotating updraft. That is the key characteristic of a supercell that differentiates it from other kinds of thunderstorms. You can have very intense thunderstorms without rotating updrafts. For example, strong QLCSs, those are linear type storms. Very intense pulse thunderstorms don't have rotating updrafts. But the key characteristic of a supercell thunderstorm is that rotating updraft. And because of that, supercells are really called that because they are the most prolific producer of significant severe weather, really, that exists. I mean, I guess you could say hurricanes produce widespread wind damage, but those are different classifications of storms.
Right. In terms of the proportion of supercells that produce severe weather compared to other types of severe weather, it's very high. Like pretty much if you have a supercell, you have severe weather almost by definition.
Yes. So, again, the definition for severe weather in the Weather Service sense is wind gusts greater than 50 miles per hour, 1 inch or greater hail, and or a tornado.
Right.
And because of the rotating updraft, the majority of significant tornadoes, at least greater than EF2 or greater in rating, come from supercell thunderstorms. You also get a large proportion of your significant hail reports greater than 2 inch or greater.
Yeah.
Those reports are generally from supercells.
Yeah, you pretty much can't get gigantic hail from any type of system except a supercell.
Yeah. The
dynamic
updraft speed.
Yeah, the updraft speeds aren't there, and pulse events and other factors aren't there. You pretty much only get large hail from supercells. So,
and fun fact about supercells, they can be both cyclonic, which means the mesocyclone is rotating counterclockwise, and anticyclonic, which means it is rotating clockwise.
So you said a word there, mesocyclone.
Yep.
So that mesocyclone is what we're talking about with the
Rotating updraft. Yes. And it's bigger than the tornado scale, but it's smaller than the storm itself.
Right.
So it's kind of in the middle of that spatial size.
Yeah, they're going to be a few kilometers wide.
Yeah.
Generally, they could be wider than that or smaller than that, but that's kind of the scale they're on, is a scale of a few kilometers.
Yeah.
So that's that area that's purely rotating.
Yep.
It causes that distinct hook that we generally see in radar reflectivity. So it looks like kind of a comma.
Yeah.
Where there's an area of lower reflectivity, and then usually you get a tornado that forms somewhere near that hook, because that's basically right underneath the rotating updraft.
Yep.
Okay, so what else about supercells?
Man, they're really fun to study. They're really fun to look at on radar.
Yeah.
They're very hazardous.
Right.
So, and you can have, supercells come in, all shapes and sizes. You can
I was going to say one of your personal professional interests are supercells in lines, just to confuse everybody.
Yes, we're going to talk about this later, but I am a huge fan of studying supercells in line, which is just basically a fancy word for a squall line that is driven by a persistent supercell. So it has a persistent mesocyclone in it, or persistent rotating updraft, but it's in a squall line. It's kind of confusing, but those are very, very prolific at producing tornadoes. And of all tornadoes produced by linear systems, they produce the most strong tornadoes.
Yeah. So supercells don't have to be isolated.
Yeah.
But they can be within greater structures. But there's still a mesocyclone.
Yes.
That's in there. So if you have a supercell in line, you're going to have supercell that has a mesocyclone within an area of thunderstorms that don't have mesocyclones.
Yep.
So let's talk a little bit about how they form and what you need to get those formed. So you want to talk a little bit about the wind shear profile you need?
Yeah, so you're typically going to want winds that are increasing in speed with height so that you get efficient. If you're looking at the ground, if you're looking straight across a ground plane and you see like 1 mile up, 2 mile up, 3 mile up, you want winds that are increasing with each height. So in that case, you get like a tube of air that is kind of spinning on itself.
Kind of like a pinwheel.
Like a pinwheel, as you have stronger winds at the top than you do at the bottom. So you get it to spin in sort of if you're looking straight ahead, this gets a little confusing, so bear with us. But if you're looking straight at it, it's going to spin clockwise.
Yep.
And so you really want an environment that's heavy in wind shear. You also need a favorable environment when it comes to instability.
Right.
Supercells don't have to produce tornadoes. You can have a favorable instability environment without a favorable low-level moisture that would yield a tornado. You just need enough instability to get the storm to rise and take advantage of that.
Right. So you get that pinwheel, and if you have instability and an updraft, that basically turns it in a different axis. And then as you have instability, that air is going to accelerate as it rises, and it basically stretches that pinwheel. And it kind of works like the ice skater angular momentum thing, where you have your arms out, you spin, and if you pull your arms in, you spin faster.
Yep.
That's basically what's happening as the instability stretches that pinwheel, and that's what effectively creates mesocyclone.
Yeah. If you're at a desk we have spinny chairs in this office. If you're at a desk where you can spin around, just try this for a second. Spin yourself and have your arms out, and then pull them in. As you pull them in, you're going to spin faster.
Right.
So that's the same process that's at work here.
Yeah, so you can look up the vorticity equation in any meteorological textbook, and there's a couple different factors that go into that. And we've been mainly talking about the stretching and the tilting of that horizontal wind shear.
Into the vertical plane.
Yeah,
yes.
The vertical horizontal wind shear into the vertical plane, basically.
Yep.
So yeah, that's basically the two things you need, is that wind shear to a certain amount. Generally, you're going to want more than 40 plus knots of 0 to 6 kilometer wind shear, somewhere in that range.
Yep.
And again, like Pierce mentioned, you don't need low-level wind shear or low-level parameters to be favorable for tornadoes to get a supercell.
Yep.
You can have supercells that don't produce tornadoes at all, and they don't produce any real circulation at the surface. They are mainly aloft. It can still produce big hail and potentially downbursts and stuff.
Yeah, the coolest thunderstorm I've ever seen in my life was not even one that produced a tornado. I saw it on the plains back in 2017, and it was just producing some honking hail, but it didn't produce a tornado, but it was just, you could see, it was probably, a kilometer up. You could see the storm itself rotating as it ingested air from that strong mesocyclone that was driving the thunderstorm's intensity. And it didn't produce a tornado. It tried at one point, but it just produced some honking hail. It was crazy.
Yeah, some of the most picturesque storms are high plains supercells. They get out like in Montana, North Dakota, South Dakota, where the air is pretty dry at the surface, but they're able to get supercells that form due to the profile aloft and stuff. So you'll have these really high base supercells that are not producing tornadoes, but can throw some big hail out, and you can see the whole thing. The mothership kind of profiles and stuff like that.
That's so cool.
They're very, very cool looking.
Yeah, if you want a picture of this, look up on Google LP supercell.
Yeah, low precipitation supercell.
Yep.
There's a whole spectrum of supercells. You have your classic supercells that are the ones that generally produce the more strong to violent tornadoes, just because there's more parameters in place. And then high precipitation supercells, and those can
common
also,
in the southeast.
Yeah, high precipitation supercells are generally what we get pretty much east of the Mississippi, just because there's a lot of extra moisture. High precipitation supercells can produce tornadoes. They do all the time. They produce tornadoes, at least strong tornadoes, more often than low precipitation supercells will produce strong tornadoes. So.
And the tornadoes that are associated with those are rain wrapped, so it's pretty dangerous.
Again, like we get in the southeast. So kind of going into the geographic span here. Supercells happen most often in the plains, just because that's where we get those wind shear profiles and the instability most often line up. There's also less to interfere with supercell production out there. You can see them from farther off. It also makes them more visible. So they happen most common out there. We do get them in the southeast. You pretty much get them everywhere in the country. I'd say it's pretty rare to get them on the west coast. But
part in the northeast too. It's pretty rare up there.
Yeah, occasionally they do though. They'll get more like linear supercells up there that form in lines. But yeah, pretty much anywhere east of the Rockies can get supercells. They're just most common in the plains.
Go.
Okay, so now we're going to move on to our interview with one of our managers here at the Columbia office, John Q. We'll let him pronounce his full last name. So John, welcome to the set.
Thanks for having me.
Woo! We always clap. We always clap for our guests.
All right, so let's start off with the last name. It's John Q, which stands for Quagliarello.
Quagliarello, pretty close.
Quagliarello. Okay, there we go.
There we go.
That was pretty good. Nice work, Matt.
It is definitely the hardest name to spell and pronounce in the office. So.
I agree.
So, it is what it is. So, John, where are you from? How'd you get into weather? Tell us about your job.
So I'm originally from Long Island, New York, and I think my interest from weather started with Hurricane Gloria when the eye wall passed right over my house when I was a kid.
Nice.
And then, so that's kind of started it.
It's like Hunter.
I think everyone has a weather event that got them into meteorology.
Yeah, that was like Hunter with Hugo.
We have 2 hurricanes. We got a snowstorm with me, and then Pierce was a tornado. So.
Yeah, I like the tornadoes got me into it. So yeah, that's cool.
Yeah, so you're the WCM here. Tell us a little bit about what that means.
Yeah, so warning coordination meteorologist. It's the worst kept secret that I think it's the best job in the weather service, but it's really we're kind of a liaison with the public, with the outside partners, and it's just a really fun job. We get to work a lot with preparedness and outreach within the communities that we serve. Get to build relationships with a lot of the key decision makers in our communities, so the emergency managers, other agencies, state and local level. So it's just, really getting out there and getting to meet people, interact with them. And then, of course, when we do have weather events coming in, I'm one of the primary people that would kind of work to provide support in terms of making sure they're getting all the products and services they need so they can make the proper decisions to really serve the public. Yeah,
we've said that you're the public face of the office. A lot of times, and it really is true. You'll do briefings with the governor, and you'll be on TV doing broadcasts and press conferences and stuff like that. So it's pretty cool. It's a cool job.
It's a fun job.
Yeah,
and I still get to forecast once in a while. And Be involved in the exciting weather aspects of things. So it's exciting.
And you get to tell us what to do. So.
Yeah, that's true. You do.
That's the best part.
They're writing us in.
Okay, so you said you got interested in meteorology with Hurricane Gloria. So what's your path to the Columbia office through the Weather Service?
So when I grew up in Long Island, I went to Stony Brook University, which is a smaller meteorology program up there, and I had the great opportunity to volunteer at both our Eastern Region headquarters and our New York City forecast office, which is actually located on Long Island. So I've got about 4 semesters of volunteering experience, and that pretty much opened the door for me to get into the Weather Service. And I started my career in the Philadelphia Mount Holly office up in New Jersey.
Shout out to Philly, as usual.
Yeah, Matt's home territory there. So that was a busy area, a huge population. I think it's the second or third largest forecast area by population, big media markets.
Oh, wow.
A lot of weather from the Pocono Mountains to the beaches in Delaware. So
that's cool.
Got to experience that and kind of worked my way south. Went to Wilmington, North Carolina as a forecaster, and then Charleston, South Carolina as a lead forecaster, and now here in Columbia.
So how long have you been in South Carolina specifically when you started Charleston?
So I started in the Charleston office in 2006.
Cool.
So been in South Carolina now quite a while.
Yeah, definitely. So what are your career events? What's like when you think back on your career, what's like the big events, both, let's say for your whole career, but then in South Carolina? What are the big events that you've worked?
Well, there's a couple. If I think severe events, I actually think we had a big outbreak back in 2008 in the Carolinas. Big severe weather outbreak kind of stands out to me. Of course, the 2015 floods. I was still in the Charleston office at the time, but that's just going to be one of those memorable events.
Yeah. That covered the whole state. There was 20 inches of rain here in Columbia.
Yeah.
Pretty crazy.
So just seeing the extent of flooding. But in terms of maybe career changing and what we've done as an office, I would maybe think Hurricane Matthew in 2016, just because of the levels for we started to provide for the state at that time. That pretty much set the stage for all the future hurricanes we've pretty much seen since then. And we've seen quite a few.
Yeah.
So connecting that there with 2016, you would have been at the Columbia office at that time. So since we're the office that's based in the state capitol, we're also the state liaison office. So we have GSP up in Greenville, that covers kind of the upstate, and then Charleston that obviously covers the coast, but Columbia acts as the state liaison. Can you tell us a little bit more about what those responsibilities are?
Yeah, so every state has a state liaison office, like Matt mentioned, pretty much where the office that is responsible for the Capitol, and really our job is to coordinate with the various state agencies. One of the primary partners we have is South Carolina Emergency Management Division, but we work very closely with other state agencies as well. So our main job is to make sure they're getting what they need from us, and we're supporting them the best that we can. So that's pretty much our responsibility. And in that process, we're working with the other offices that you mentioned, Matt, both, all Greenville, Spartanburg, Charleston, and the Wilmington, North Carolina office even, to make sure that we're all consistent and doing an adequate job giving the state and our partners there what they need.
Yeah. So what's been your favorite moment of being a WCM here? Not the biggest moment. What's your favorite moment of being a WCM here in the Columbia office?
Favorite moment?
Yeah.
That's...
Other than hiring Pierce and I.
Oh, true. Facts. Yeah, that was a big moment.
I do have to say we do have an amazing staff here. But
true.
I think favorite moment. I think I would say probably supporting the state, again, with Hurricane Matthew being the first one, because when you're there on site with our partners that are making decisions and you're providing information, and then you see the response to that information,
cool.
You see them taking action on the information that you're providing is pretty powerful to kind of see everything taking place.
Yeah.
Yeah, especially with events like that where there's millions of people impacted. You're actually seeing the direct impacts of your forecast live.
We don't get to see that from the office much. A lot of times you do a forecast and you go home and you don't know how people use that information and how it benefited people, or sometimes a wrong forecast, how it maybe had a negative impact on people. But to be there in person and see that, it's pretty powerful.
Yeah. That's pretty cool. So one thing we asked Hunter, we want to know where you're at on the weather nerd scale. So, Matt and I, as we've discussed, we're pretty hardcore weather nerds.
So outside the office, we're still watching the weather and geeking out at stuff happening in Oklahoma or wherever. So where do you fall on that scale?
Are you more a professional meteorologist, neutral, or are you like a weather nerd?
I will say we're all professional meteorologists.
Yes, of course, yes. But you keep it strictly at work.
Yes.
No, I'm probably somewhere on the middle of the scale. And for various reasons. I think I used to be more of a weather nerd back in the day. But I think more and more you see events, things aren't as...
Interesting.
I wouldn't say interesting, but your bar for an exciting event.
Oh,
That
yeah,
goes
yeah,
up
yeah,
each time,
yeah.
So, but as you kind of move along in your career, especially you start getting families and everything else too. Your time outside of work gets occupied with other things. So I'd probably say I'm in the middle of the scale, and I do need to keep up on the weather even when I'm not in the office because we can be contacted by emergency managers or other parts pretty much at any time. Needing some kind of information and being able to know what's going on in the system is important too. So I do have a love for weather. It's just probably not quite to your level of nerdiness.
Yeah,
that's fair.
Yeah. We're on the we're pretty much on the weather nerd side, as well as being professional meteorologists. So
freewheeling, one last question here for any aspiring future weather service employees out there. Is there any one tip you would give to anybody in high school or college right now who wants to work for the weather service?
Yeah, it's a tough field, believe it or not, to get into the weather service, and you really have to find ways of standing out. So a big part of it might be volunteering with local weather service offices, being involved in organizations when you're in college, weather, of societies and things like that, attending conferences, and really making relationships with people. I think that's a really big thing. Is just it's not necessarily who you know, but people could guide you along in your career. So if you can make the right connections, it's certainly something that can help you out, giving you advice in terms of applications and what you need to be doing to be competitive for these kind of jobs.
Networking, very important.
Yeah, it's not my favorite thing to do, but it's essential.
Yeah,
really, to get a job.
It's a life lesson in general.
Yeah. I have two more questions, actually.
Wow, two more.
Yeah, two more. They're related to the famously hot weather takes.
Oh,
recently.
gosh. Okay, well.
John, what's your favorite cloud? And what's your least favorite cloud?
Yeah,
favorite cloud. That's a tough one.
I didn't like lenticular clouds.
Which was, I think he's just being contrarian.
No, they're lame.
Yeah, you guys are too fancy for your cloud types. I think basic. I think my favorite's probably cumulus.
Yeah.
It just takes on many forms. It can eventually become a thunderstorm or something really cool like that. And my least favorite's got to be stratus.
Stratus is difficult.
My least favorite.
There we go. The anti-stratus club.
Yes.
Stinks for everything.
And then what is your favorite and least favorite season?
Yes.
My favorite season's probably the spring.
Yeah.
I enjoy the longer daylight. I enjoy the warmer temperatures. We get more organized severe weather. Not that I like severe weather in terms of impacts, but in terms of meteorology,
forecasting
it's
and radar.
kind of exciting to watch, and it's amazing kind of seeing what nature can do. But my least favorite's probably winter. I don't like the short days. I don't like the cooler weather.
Yeah.
I don't mind a winter storm once in a while, but it's the other days that I can do without.
Yeah. Oh, cool.
Great minds, John.
Yep.
Yeah. Stratus and spring.
That was you.
We line up with that.
So, okay, well, thanks for coming on here, John. We really appreciate it.
Thanks for having me.
Woo!
All right, so coming back to severe weather now, we're going to give just kind of a general overview about why we tend to see more severe weather in the spring, at least for most of the U.S. So Pierce, tell us why we generally see more severe weather in the spring, even though it can happen any time of the year.
Yes, it can. Generally, we see more because there is a greater temperature difference across the northern hemisphere. What I mean by that is we're coming out of winter, and the sun angle is getting increasingly higher as we get towards spring, and then we get towards summer when it hits its peak angle over the northern hemisphere. The Earth is tilted towards the sun at that point. The northern hemisphere is, at least. So in the springtime, we've got differential heating because the sun angle is still very low across the northern portion of the northern hemisphere, where they're not getting equal amounts of sunlight to the central and southern portion of the northern hemisphere towards the equator. And so it's still cold up there while it's getting increasingly warm across the Caribbean and southern United States and stuff. And so the large-scale temperature differences there really help to fuel a stronger jet stream across the northern hemisphere. And because of that, we tend to get more troughs and ridges and stronger jet streaks, which leads to stronger wind shear. And also by this point, you're starting to get a little bit more northerly low-pressure tracks. So you're not getting cold fronts that clear out the wellspring of moisture across the Gulf of Mexico. So as you start to get into March and April, the Gulf really doesn't get cleared all that often, and so you've got just this big plume of moisture available to any low-pressure system to draw on. So really those two things combine to create more active severe weather in the springtime across the United States.
Yeah, and then to kind of go along with that, the atmosphere aloft, it takes a long time for the heating from the surface to actually make it aloft. So in the spring, yeah, we can warm up pretty good at the surface. You can get, across the southeast in the 80s or the 90s in the spring.
Yep.
But the air aloft is somewhat kind of separated from that warming at low level. So it can remain cold there. And because you then have warm air below cool air, you have a buoyancy gradient that develops, and you have a potentially more unstable atmosphere. Again, this is just sort of on the whole, holistically across the United States. It's a temperature gradient from north to south, and then a temperature gradient from the surface aloft that kind of primes the atmosphere for more potential severe weather. So yeah, then we talked a little bit about the wind shear. When you get temperature gradients in the atmosphere, you also have pressure gradients based on PV equals nRT. Ideal gas law kind of governs most things.
Beautiful. What a flex there. Let's just note this flex.
It's a low flex.
Yeah, that was a good flex though.
But basically, when you have temperature gradients, you're going to have pressure gradients, and when you have pressure gradients, you have changes in wind speed. So you get more wind shear as a result of those temperature gradients. Again, if you're into that kind of thing, you can look up thermal wind. That's a thing.
It's a thing, but is it a thing? It's kind of like
it's not actually.
It's kind of like an imaginary number.
Yeah, it's a mathematical thing that kind of tells us how
it exists, but it doesn't.
Temperature gradients govern the atmosphere.
Yeah, they do. That's a fact.
Shout out to a professor I had who said you can't fly your kite in the thermal wind because it's basically just a mathematical expression. So, but it explains a lot if you're interested in such things.
Yes.
So what else about severe in the spring? Why else do we see it? Well, I can think of one. You generally have more vegetation that develops.
True.
This applies more out west where they have tons of ag, but when you get more vegetation and more leafing and stuff on plants, you have more evapotranspiration that can occur in the afternoon. So as those plants heat up, sunlight hits them, you can get more moisture that gets into the atmosphere from plants themselves. That's one thing that happens in the summers too, obviously.
But it's also after the wet season for much of the central and eastern U.S. The winter time, we get a lot of snowpack in the central U.S. and rainfall in the southeastern U.S. So got more soil moisture to work with too.
Right. Yeah, that could play a role too with if you get a big snowpack out west, you can have more cyclogenesis that occurs kind of downwind of the Rocky Mountains. Just because again, you're going to have more temperature gradients that develop from cooler air off the Rockies with the warmer, moist air from the Gulf of Mexico. It's pretty much everything becomes more favorable in the spring for severe weather across most of the United States.
Prime time. And geographically it shifts too, as the basically from like, let's say late February right now through, mid-June, you'll see a geographic shift you can actually see this on, the Storm Prediction Center's website where they've got where climatologically severe reports are like each day of the month for all the year. You can see it shift from the southeast in the early portion of the spring, spreading over much of the central U.S. by the late April, early May, and then starting to gradually shift north by late May, early June.
Yeah, and the cool season, from like November through February, most of the severe weather that happens is in the southeast. Because we don't get a lot of it in the cool season, but we can get it. They don't get much severe weather at all in the plains, in the northern plains especially, because it's just too cold and too dry.
We've got very easy access to moisture.
Yeah, so that's why in the cool season, it's generally in the southeast, and then it increases in frequency pretty much throughout the entire country in the spring. But it turns more towards the plains. So. And I think that's a pretty good wrap on a broad overview of spring severe and why we see it. Again, this is kind of part one of our April 27th episode. Again, we don't have a huge connection here in Columbia. Georgia had some tornadoes from the April 27th day. It didn't impact our CWA very much, thankfully. But again, it was such a big event. It's probably, fingers crossed, the biggest event for our lifetimes.
Oh, yeah, seriously.
It's right up there with the super outbreak from 74, 72. Can't remember the year there, but it was a once-in-a-generation event, hopefully. We would definitely not like to see that again, but it's definitely worth talking and doing a full episode on.
Okay, now we're going to jump into one of everyone's favorite segments, maybe the best segment ever made, honestly, our famously hot weather takes. So, Matt, let's hop in the weather sauna. Let's drop some hot weather takes right now on the people. So what are we talking about today?
Okay, so our hot weather take today is going to be on our favorite and least favorite storm morphology. And by storm morphology, we mean either pulse, linear, quasi-linear, which is the QLCS, or supercell. So those are the four kind of main general areas of convective storm morphology that we see. Yeah. So Pierce, what is your favorite to either forecast or just watch?
My favorite to watch is probably pulse because I can most often watch it. My favorite to forecast is certainly in the family of QLCS. We talked about it earlier this episode. It's in the family. I'm going to take a cop out. 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 And I'm going to choose Supercell in line. So basically I'm combining two morphologies right here. So
why do you find those interesting from a forecasting perspective?
Well, from a forecasting perspective, they're very challenging to forecast. But they are the environments are similar to that of supercells and lines. But they're also really, really, I don't know, they're just interesting to me. I've become extremely interested in them. They are, anecdotally, they're extremely prolific at producing tornadoes. So oftentimes the mesocyclone that's within them will grow upscale into a mesoscale vortex, which is a larger scale vortex over a larger area. And within that, it increases vorticity and can often increase the wind shear immediately ahead of it and really leads to prolific tornado production. I just find that very interesting. I don't know. Radar-wise, it can be a little tricky, but just knowing, knowing the things to look for in mesovortex generation within QLCSs, knowing the environments these things form in, you can kind of beat it, so to say, put that in air quotes. You can kind of beat the system and figure these out ahead of time.
Yeah, most of the big tornado producers we have around here, we don't get many discrete isolated supercells.
Yeah.
Occasionally, I think March 15th, 08.
Yep.
That was a pure discrete isolated supercell day.
April 4th or April 5th last year.
April 5th last year down in Orangeburg. And
a good example of a supercell line event is April 13th, 2020.
Yeah.
Orangeburg Tours.
And the one that we had Hunter on a few weeks ago to talk about that.
Yeah. That was a significant supercell line event here. The environment was completely ridiculous, especially in the middle of the night. And you had kind of the ultimate example of a supercell in line over, what was it? Walterboro County in Charleston's area?
Yeah, the one that produced the EF4.
Yeah, producing the EF4, and on radar, it's just unbelievable. It looks like a supercell that was literally copied and pasted from the planes and planted into
the middle of a line. Yeah.
So I just find the way that I find their morphology very fascinating, the amount of tornadoes that they produce. They can often produce tornado families. That produced a tornado family across the low country of South Carolina. December 12th, 2021, Bowling Green, Kentucky tornadoes.
Yep.
300-mile long tornado family from one supercell that ended up developing into a line. Just really, really interesting morphology.
Yeah, they're cool from a forecasting perspective because they do have characteristics of both supercells and linear features where in the southeast we tend to have way too much moisture at low levels, and we get these very strong systems that cut through, and you can lift that whole line of air and get a linear system that way with a broad area of lift. But then you also have features like the deep layer shear and pretty strong instability where you can get supercells that develop out in front of that, and then they either merge or grow upscale into that line. So yeah, they're very interesting because they kind of have multiple features to them.
Yep.
And they most impact our forecast area in terms of the high-end severe weather. So,
what's your favorite? To forecast and just to watch.
Again, I don't want to flex too hard and be that guy, but I did flex. My grad work degree was all on supercells and their behavior during the nocturnal transition, which is just sunset, and how they behave with that. This with my advisor up at UNC Charlotte. So. I really like supercells. They're very interesting.
Yeah.
They behave. The translation from what physically should be happening in a pure mathematical sense, it translates to the real world in kind of a uniquely
weird,
accurate.
Oh,
yeah. It's with most meteorology. It's we can make all these simplifications to what is going on in the equations, and the real world's much messier. But supercells behave just like the math says they should, where you get splitting supercells and you can derive all that stuff in your dynamics class. and they really behave in almost idealized sense, especially out in the plains where you have just big open fields where they occur over. There's not terrain or lots of vegetation and stuff that can inhibit that. So supercells are pretty awesome. That's the lame one. I really do like just pulse events. They're really cool.
Watching them or forecasting for them?
I like watching them.
Yeah.
Yeah, I can just sit on my porch and listen to rumbles of thunder. And
yeah, it's nice.
It's kind of cool. I have a nice kind of overlook from where my house is, and I can see pretty far off to the northwest. So
that's nice.
You watch them out there, you can see kind of downbursts happen. And,
that's cool.
Kind of stinks because you're sweating the whole time you're watching them because it's 98 degrees out.
You should get a fan.
I do have a fan.
Oh, but even better.
Yeah, it doesn't work that well. So.
You need to get one of those fans that like sprays the water and
that'd be cool.
zoos.
Yeah, that'd be cool.
My least favorite.
Yeah.
No, go ahead. Sorry.
Go ahead. Yeah.
I was going to say my least favorite to forecast for. Also happens to be pulse. I hate working radar and pulse. I don't hate it because I love working radar pretty much no matter what. But working radar for pulse is just such a pain in the butt because...
So pulse is the opposite of supercells in any sense because they don't behave. Yeah. It's literally like you're just taking the earth, like your boiling pot of water. The hot surface pan is the earth.
Yep.
And those bubbles that are just going crazy, those are your pulse convection.
Yep.
They just happen randomly,
and
they're almost impossible to forecast at more than a half an hour ahead of time. You're watching. I mean, just tell us about how brutal it is.
Oh, it's really annoying. I mean, you'll have one storm that you'll be looking on radar, you'll be looking for certain things, and you'll have it hit. And, you'll be like, oh, certainly, this needs a severe thunderstorm warning. And you'll get 0 reports from that. But then you'll have another thing go, and you'll have, you'll put a special weather statement on it and be like, oh, this isn't anything. You'll get reports out of that. You have to almost have to completely readjust what you were expecting because pulse is just it's just so difficult.
Yeah, it's very random.
Yeah.
It is fun to forecast because it's exhausting in a way.
Yes, it is.
You're just on
all day.
For as long as there's heating,
fast.
It goes. Things kind of fly by, and you're constantly engaged, which is kind of fun. But it's
a challenge.
Yeah, it's one of the ones where you're constantly switching from visible satellite, looking for tiny cumulus areas that are popping up, and then looking at the environment, thinking, okay, this is along a differential heating boundary. You can have this pop here, and it's just it's kind of a mess.
Yeah, you're really trying to figure out most of the afternoon and evening why this didn't produce anything, but why this did produce something, why this didn't, etc. I mean, you're really just... Sometimes you're pulling your hair out.
QLCS stink too. Yeah. I think they might be my least favorite.
Really?
To forecast for.
Interesting.
Because Pulse at least doesn't produce tornadoes 99% of the time.
Yeah.
But QLCS is due, and unfortunately we just saw, we're recording this podcast in late February, they just had that QLCS tornado that ripped through Norman, Oklahoma, and kind of late in the evening with that first round of severe weather that happened, and that was at EF2.
Yeah.
And they can produce strong tornadoes even though they generally don't. And the randomness that's associated with the strength of tornadoes and QLCSs is tough to forecast.
So I don't know. You have anything else?
I don't think so.
You have any other spicy weather takes in the weather sauna?
No, I think we're gonna have to leave the weather sauna. We're both dehydrated.
I know. Now. That has been your famously hot weather takes with Matt and Pierce. So
this has been Pierce.
So I think that's all we have for this episode. Well, thank you all for listening. As always, please like and even maybe subscribe to our channel if you could. Please like and subscribe. Leave a comment. Email us. Tweet us. Call us. Fax us. Whatever you need to do to get your questions into us. And if we have any more questions later on, we'll answer them.
Write us letters.
Write us letters, yeah.
I'm a big pen and paper guy.
Yeah,
so.
True. You do have like a little notebook that has stone paper in it.
I do, yeah.
Yeah, it's kind of crazy.
Write letters. It's great for the mind.
Yes, it is.
So
okay.
All right.
Adios, everybody.